Right, so welcome everyone to this third talk in the series of quantum partial differential equations. And it's a pleasure to have today Avy Soffer from Rutgers, who's going to talk about dynamics of NLS with bounded initial data. Thank you, Avy.
Thank you. So first, I would like to thank the organizer for the opportunity to talk now. And so this is a subject which is basically we have preliminary results. What I'm going to talk about is based on two papers that we did in this direction. And so I would like basically to present this, this kind of circle of ideas and problems and try to explain a little bit the motivation behind this kind of questions. So this is joint work with Ben Dodson and Tom Spencer. And the subject is to consider the nonlinear Schrodinger equation, say on the real line or on the lattice, with initial condition which may be smooth, but not vanishing at infinity in general. And so the question is, what can you do in this kind of situation? That's the first question. And the second question is why it is interesting and what are the kind of open problems which are related to this and how it is related to other fields. So here are the examples that I'm going to talk about. The first one is on the real line. It's the nonlinear Schrodinger equation. It could be here plus or minus. So when it is plus, it is the defocusing. When it is minus, it's the focusing. And now the initial data is assumed to be smooth, but just bounded and not decaying at infinity. And most of the time, that's going to be the assumption. And on the lattice, we will look again at the nonlinear Schrodinger equation, the cubic nonlinear Schrodinger equation. And in this case, also, we take initial condition, which is bounded. Okay, bounded, but uniformly bounded, but not localized. So what is the key distinguishing properties of this problem? Is that the energy is infinite and the mass is infinite of the initial data. So all the results in this direction are going to be very different from what we are used to. So the most basic questions are open, namely, does there exist a solution even locally in time? What are the properties of the solution? And what is the growth of a function as a function of time if there is a solution? And how this is related to other problems in mathematical physics. So that's what I'm going to explain via examples, simple examples that we can do. So first of all, let me tell you how to choose initial conditions, which are interesting. So for example, on the real line, you can take initial condition, which is periodic. Right? That's one example, simple example. And a lot is known about this case, and you will see in a moment why. However, once you take a quasi-periodic initial condition, A cosine plus B cosine where alpha is irrational, then this problem is much, much different and very difficult. In fact, very little is known about this case. And the third example, which is in fact of fundamental interest, is to take the initial condition to be smooth and random. And you see, because the sum here is on the lattice, you have Gaussians which are sitting everywhere on the lattice. And so this function, this initial condition, has infinite energy and infinite mass. On the lattice, you can look at the bounded initial condition, quasi-periodic initial condition, or random. For example, you can take all the values at every point to be in the distributed, say, between -1 to 1 and independent of other points, and something more fancy, which is to take U0 in equilibrium. So this is something that will be discussed later. Okay. So what do we know about equations in which the mass and the energy are finite? We know that this quantity is time independent, and we know that the energy is also time independent. And these are conservation laws which play a fundamental role when we try to prove the existence of solutions. Even local existence, we start by using this kind of conservation laws whenever they are available. So the problem that we are going to talk about now is when these two quantities are infinite. And the question is what to do. Now, in the periodic case, you can reformulate the problem on a torus, and then you have finite energy on the torus. So this problem has been analyzed extensively by Bourgain and others. And nevertheless, even this problem has very serious difficulties in understanding, because the H1 norm is conserved in this case because we are on a compact domain, and the L2 norm is conserved. But the question is, what would be the behavior of the HS norm, the higher Sobolev norm for S larger than 1, if the initial condition is smooth? The conjecture is that it is growing, but how it is growing and is it growing forever? Most of these questions are completely open, even for this kind of situation. In other words, the problem that I'm talking about is in fact open even on a compact closed torus if you ask slightly different questions. All right. So now I would like to say a little bit why this problem is interesting and where it is coming from. First of all, from a physical point of view, this problem may correspond to, say, either initial condition, which has infinite energy, basically because of the way you use it. For example, if you have water waves and you are interested to understand the dynamics of water waves in the ocean. So the initial condition is the water wave, the surface of the whole ocean. It's basically infinite, right? And so what is the interesting question about that? Why is it, for example, that you don't have a situation in which all the energy in some huge area on the surface of the ocean converges to essentially one small region and create a wave of size 1 kilometer, right? It's not happening, right? We see rogue waves, they survive 40 meters at most, and then they disappear. So similarly, one would like to understand situations in which you start with an initial condition which is nice, and you want to see the approach to equilibrium. And in many cases, the approach to equilibrium corresponds to the solution spreads out uniformly in Fourier space. But that corresponds to the situation in which the higher Sobolev norm go to infinity. So in other words, approach to equilibrium and spreading in frequency all the way to infinity sounds like essentially the same thing. And we would like to know if nonlinear equations actually do such a thing. For example, Fermi-Pasta-Ulam is a problem of this type. So, of course, the nonlinear Schrodinger equation also appears in a fundamental way if you use it as a leading order approximation for n-body quantum mechanics. You take a big box and you put in it a huge number of particles, and then you ask how to analyze this problem. Then if you start, for example, with a product state, then you can show that for certain short time at least, the nonlinear Schrodinger equation gives you the effective dynamics, and then you would like to use that in order to approximate the second order, which is coming from Bogoliubov dynamics, and so on and so forth. Right? So in all of these problems, it is natural to ask the question of what is the behavior of the nonlinear Schrodinger equation for initial data, which is large. By the way, this is also the main issue in the main mathematical issue in trying to understand the derivation of kinetic equations. For example, in wave turbulence and kinetic equations which appear in this kind of situations. So there are a lot of works in this direction. I put here few names, and so in many cases, with a good choice of distribution of initial conditions, which is random in general, the problem is reduced to rather hard analysis which requires estimating the lot of diagrams, Feynman diagrams, and counting them, and so on and so forth. And so far the situation is that it is almost impossible to prove that you get the kinetic equations all the way to the time scale where the kinetic equation is relevant, right? This is very important because the kinetic equations tells you whether the frequency spreads to infinity, what is called the energy cascade. So it's absolutely crucial to understand rigorously how to approximate the dynamics of this kind of equations by kinetic equations. So these problems are related to each other. Okay. So all right. So this is quick outline. I will first of all talk about the quasi-periodic case. Then I will introduce a crucial notion in this game, which is finite propagation speed. Then I talk about a few examples, and then I will tell you about the latest result in this direction. Okay, so let us look for, first of all, about the quasi-periodic problem. So here is quasi-periodic initial condition on the real line. And so local existence was proved for this kind of data by O. And he also was able to prove global existence for limit periodic data, which is slightly more general than periodic. So that's one class of result which is known. And then more difficult and more global result is due to Damani, Goldstein, Binder, and Lutzig. They proved global existence for small amplitude for KDV. And there were assumptions on the what is called the Ofantin conditions on the frequencies. And in this case, they were able to show that the solution is bounded and it is almost periodic. Furthermore, they used the fact that the equation in one dimension, the KDV in one dimension, is integrable. So this was also used. Okay. I'll come back to this issue of the difference between completely integrable and not completely integrable. So global existence for quasi-periodic data is not known for KDV or NLS, for large data. So for example, it is not known if you take the NLS with the quasi-periodic initial data, which is large, whether the solution will stay for all times. I mean, one would expect that not. You would expect that after finite time, the solution will become chaotic and almost periodicity will go away. But it's not known. What is known is the following result of Wei-Ming Wang, that it is possible to construct small amplitude solutions in the one dimension NLS, which are quasi-periodic both in space and time. This is based on KEM theory, and this also applies to non-integrable equations. However, I should point out that this result is not an initial value problem. So you construct a solution which is like that. It is not coming from a particular initial condition. Okay, so a key idea which is needed in order to understand initial condition which has infinite energy and mass, which is smooth, is the phenomena of focusing. And the phenomena of focusing, we know it from all dispersive equations. Basically, if you have a mass, if you have L2 known somewhere, it is moving with a constant speed. It can move with a constant speed under the free flow. And if you have pieces coming from all kinds of places together, they can all focus at one point. And then you get very large, at least for a short time, you can get the solution become very large. So if you have finite propagation speed, you see that it is not possible after finite time to bring infinite amount of mass to one point, because finite propagation speed prevents the possibility of bringing all the mass from the infinity all the way to the origin. So you would expect that when there is a property of finite propagation speed, at least at the linear level, then at least at the linear level, the solution should not blow up after finite time. So how to see that? Well, if you have the nonlinear wave equation, which is here, in this case, you have finite propagation speed also for the nonlinear equation, and you can use that to show that the solution cannot focus too much after finite time. And so one can use it that at least in the defocusing case, you can prove that the solution cannot grow faster than t to the 1/3 if the initial condition is smooth, but not localized. So this is the upper bound even in the nonlinear case. Now, this is not going to work for the nonlinear Schrodinger equation, because for the nonlinear Schrodinger equation and for KdV, there is no finite propagation speed. Frequency k propagates at speed k. And so if the nonlinearity produces more and more higher frequencies, you will have higher and higher speeds. So in principle, after finite time, all the mass can come from infinity and hit the origin, and you get blow up at a finite time. And the question is how to avoid this kind of situation, whether it is even happening. Okay, so let us first of all look at the linear problem. At the linear level, the solution, Schrodinger equation, has finite propagation speed effectively. Why? Because if the initial condition is smooth, then in principle, all the solution is localized in frequency space between two numbers. And the highest number gives you maximal velocity. And this maximal velocity can be used to compute how much mass you can squeeze into one point after time t. And so when we do the computation, this is what we got. We got that if you take an initial condition for the linear Schrodinger equation, which is a C2 function, then after time t, the function will be controlled at any point by t to the 3/2 times two derivatives in L infinity. Right? So in this case, the mass and the energy are infinite. Nevertheless, the solution will not blow up in a finite time. That's the linear case. Now, in the random case, where all the AJs are bounded by 1, and in this case, actually we get much better. We get t to the 1/2. We get t to the 1/2 in this case. And it is not possible to improve that because one can show that you can choose the AJ to be in such a way that you get exactly t to the 1/2. However, the interesting fact, something that I'll come back to it again and again, is that if you now take the average over the randomized initial condition, in other words, you randomize the initial condition and you take the average, then the solution is bounded. On average, the solution is bounded. So if you take the expectation on the AJs, then, and you look at UTX squared, then it is uniformly bounded in time everywhere. So the question that we don't know how to answer at the moment, which is true for all the equations I'm going to talk about, is the following. Is this phenomena can be used to improve the result for the nonlinear problem? So if you take the nonlinear problem that you like, anything you want, and you say, okay, under the condition that I am randomizing the initial conditions and take the average, can I get a result on global existence or on the size of the solution, which is better than the nonlinear equation, that is better than any initial condition, right? So you see that at the linear level, there is always an improvement. The question is, does it survive the nonlinearity? So first of all, I would like to just say a little bit about how one proves the result even in the linear case, because it shows why the finite propagation speed enters, right? So basically what you do is you collect all the pieces that contribute to the point X by partitioning the space into blocks of size 1, basically. And each one of them is around the point J. And then what you have to show is that the contribution of each point to the point X is from a distance J decays like the distance faster than 1 over the distance, times some polynomial in time, times some smoothness, right? So if you can prove this, then you are done, because then you can take the sum over j, it will be fine. So that's how finite propagation speed enters here. It enters because if you are far away, you cannot get contributions too much after a fixed time. So this estimate can be proven by, because this is just for free flow, so it can be proven by stationary phase integration by parts, or you can prove it by a more abstract way, which is by looking at how x times e to the it Laplacian f0 grows as a function of time. And then you find out that this is controlled by the commutator of x with the Laplacian. X with the Laplacian is the derivative, that's velocity. And since under the linear flow, this is bounded, if the initial condition is bounded, then you see that as long as you have finite propagation speed, you get a control. You get this grows at most linearly, and this is what is used in order to prove the estimate in another way, right? The problem is that this argument will not extend to the nonlinear case, because you cannot prove boundedness of the velocity of the frequency. Okay, so then to make life simple, let's go to NLS on the lattice. What is good about NLS on the lattice is that there is finite propagation speed. So you would think that because there is finite propagation speed, this should be exactly the same as the wave equation. Okay, so now let's see if it's true. So you have the finite propagation speed because the Laplacian now is a bounded operator. And indeed, we can prove that if the initial condition is bounded, then in the defocusing case, it grows like t to the 1/4 at most. And moreover, we have an estimate also on the energy, that the average potential energy is uniformly bounded. So this is a box of size t. So now here is already, I can point out to the first non-trivial question that appears. I mean, this system is the simplest I can think of, which is not completely trivial. And even for this system, there are many, many questions which we don't know how to answer. For example, what happens when t goes to infinity? Can you actually prove that the energy per unit volume on a sufficiently big volume converges to a constant? And what are the fluctuations in the energy, right? So we know that it is uniformly bounded, but we don't know how to prove that it has some kind of a limit as t goes to infinity. In other words, does this system approach some kind of equilibrium? We don't know. In the focusing case, the proof does not work, and you only get t to the 1/2 growth in the focusing case. But in the defocusing case, you get t to the 1/4. So let me explain the idea of the proof, because it is kind of instructive. And the next question would be how to generalize this kind of an argument to the case when the initial data is randomized. We know that for the linear problem, if we randomize the initial data and we take the average, the solution is bounded for all time. The question is whether we can get rid of the t to the 1/4 by taking average over random initial data. We don't know the answer to this question. So how to prove this? It's non-trivial. So what you do, you are going to use an approximate conservation law. You say, okay, if the initial condition was in L2, then the sum of u squared is constant in time. Since the initial condition is not in L2, we are going to put a cutoff function which localizes us in a ball of size r times t0, basically. And we are going to choose this cutoff function in such a way with parameters which are such that we are going to derive now an approximate conservation law for this local mass. And you just do the computation, and you use the fact that the Laplacian is a bounded operator, and you get an inequality, nice inequality, and you see the derivative of the L2 norm is 0 with respect to time. So in fact, all the contributions to the derivative is coming from the when you take the derivative of the function f. So this gives you the two types of contributions. One, it is derivative with respect to time of this function, and another is the commutator of this function with the Laplacian. Since the Laplacian is bounded operator, we can estimate everything by we can estimate the derivative in this way, and so we can solve this inequality, and we get that at time t0, m at the mass at time t0 is bounded by the mass at time 0 divided by r, and moreover, you can see that this m of 0 is very big because it is coming from the L2 norm on the volume r times t0, and from this you get t to the minus half growth, which is true whether the nonlinearity is focusing or defocusing. You always get t to the minus half. So this gives you t to the 1/2 growth of the L infinity norm. In order to get the t to the 1/4, you have to use exactly the same idea, but instead of local mass, you do local energy. So you do the same thing on local energy. The computation is more involved, but in the end of the day, you get a similar estimate on the energy, which implies something similar to this, and therefore you can get the time average of the L4 norm is uniformly bounded, and from this you get the t to the 1/4 is bounded. Of course, if the power of the nonlinearity is higher, the growth is lower. So in other words, if you take instead of u cubed, you take u to the 5, then you will get the L infinity norm grows even slower because you have more dispersion due to the defocusing. So for those who do propagation estimates in scattering theory, you may realize that basically this is some kind of an observable which to leading order has a nice sign for its derivative with respect to time. Okay, so now I want to say the following, that we don't know. So we don't know how to put this simple quote argument, how to put this to work in the case that the initial data is randomized. So how to put the two pieces together, it's not clear, right? This is something that I did not see before. Okay, so the next example that we were able to do is to say, okay, now we want to solve the problem in the continuum, but in the continuum, the nonlinearity is going to destroy us. So what we are going to do, we are going to smooth out the nonlinearity. We smooth out the nonlinearity in a brutal way. We take the function u and we smooth it out by smoothing it by convolving it with a function phi of x, which is smooth and symmetric, for example, Gaussian. And then we construct the nonlinearity out of this smoothed out function. This is a translation invariant problem still, because we are only localizing u in Fourier space. Okay, so now let's see what happens. If you take u0, which is C4, then we are able to show that the solution grows at most like t to the 8/3. Right? So the proof uses the same argument as before, but it is much more complicated. You localize the energy in a ball of size r, and then you have to study the time behavior of this, but it turns out to be very, very complicated because the nonlinearity actually drives the frequencies to infinity in this problem, and you cannot avoid it. But what you can do is you can control the rate at which these frequencies grow. And if you can control the rate at which the frequencies grow, by a polynomial, then you also get the energy and the focusing grows like a polynomial. And this is where the t to the 8/3 comes from. But the proof is pretty long. It is based on this idea. Once again, the cutoffs are such that you get good sign for the derivative with respect to time, modulo corrections that you have to control. Okay, so the next example that we could do is local existence of rather general initial data. So we take an initial condition which is bounded and analytic in a strip of some constant width, let's say 3. So this includes the examples of random, smooth random or quasi-periodic data. So all of these cases fall under this kind of example. And now what we did was to apply a Newton iteration scheme to solve this problem. So in other words, you first of all take the free solution for the problem and you linearize around it. And then you write you linearize around it, you get some kind of a correction. The linear equation for the correction is this one. Everything else is in R1, which is this one. And now you solve for C2. And how do you solve for C2? Well, it's linear. So first of all, you solve the linear problem. The linear problem is not self-adjoint anymore. The linear problem is not self-adjoint anymore. You see there is C2 bar here. So since it is not self-adjoint, you can have arbitrary growth, exponential growth, for example. So so now you want to solve these equations. And so you solve the equation for C2. And then you say, okay, U2 is going to be U1 plus this C2. And then you write down the equation for C3. And you see that it looks essentially the same, right? Essentially the same, the linear one, plus R2. So where is the action coming? So the action is to see how to control these correction terms. So here is the formula for the correction terms. You see, what is good about the formula for the correction terms is that it is quadratic in C2. So since it is quadratic in C2, if C2 is small, then we can use Newton's scheme to solve the problem. And so that's what happens. We use the fact that this equation is quadratic, and therefore we can do iteration, which is basically following Newton's scheme. This is an iteration which converges super exponentially fast. But in order to do the linear problem, you have to deal with the fact that the linear problem is not self-adjoint. So you have to complexify things, and then you get the diagonal part is the Laplacian. And then there is a perturbation, which you see is not self-adjoint because of these two terms are not equal. And now you have to get an estimate on the growth rate of this linear problem. So, so you get an equation. You get an equation for the iterates, where this matrix M is the fundamental solution of the linear problem with this matrix problem, right? So you have to solve this, and basically you need to control the growth of the derivatives. And this means that basically you need to do the commutator of the derivative with the fundamental solution. So you can write it explicitly like that. And all these things basically give you a scheme which you can use in order to prove local existence. So what you can prove is that there is a solution for a finite time which remains analytic, not in the same strip, in a smaller strip. You keep losing size of the strip. This is similar to what happens in Nash-Moser schemes, that you keep losing analyticities when you do the iteration, and so that's why it stops after finite time. So this means that, for example, it is slight. This result is more general than the original result of OR, about quasi-periodic solutions, because this is telling you that practically any analytic initial condition, you get local existence. What is not yet done is, for example, just to show you the complexity of this situation. For example, many people looked at the problem of the nonlinear Schrodinger equation with initial condition which is equal to the constant function 1 plus a small perturbation. So you can do the constant 1 plus small perturbation, but you are interested now in a perturbation which is not localized. It's small, but it is spread all over the world, like this initial condition. And then you see the function 1 is also analytic, so you can apply this method. If you apply this method directly to 1 plus epsilon, you will only get existence for a very short time. The question is, can you show that if the initial condition is 1 plus epsilon, then the lifetime is of order 1 over epsilon, let's say, or 1 over epsilon squared? That would be much more interesting. By the same method, using the same method. Okay, okay, so this is basically how you see how the Newton scheme works for you, because you get something which is super exponential, which is used to knock off the n factorials that appear in the iteration scheme. So about the linear problem, basically what we did is to use something very simple that says that this fundamental solution grows exponentially. Grows exponentially and not more, depending on some norm of the potential term. Of course, this is not the best possible, but this is this is sufficient if you just want to prove local existence. Okay, so everything I discussed so far was in the first paper, and now I would like to say a little bit about a second paper that we just completed, in which we prove a result which is kind of surprising, because it works for the nonlinear Schrodinger equation without any cutoffs, and for a smooth initial condition, which is basically has arbitrary slow decay at infinity. So the result says that if, at least in one dimension, although the proof looks like it is general, if you take the NLS, in one dimension with initial condition, which is smooth, and satisfy, and it is in some LP space, right? It is smooth and it is some LP space, then you have global existence. Then for all times, the solutions stay in that space. So now let me take a special case. The way we prove it, we start with L6. So the proof is based on some kind of iteration. You prove it first of all for L6, and then you go from L6 to higher norm and higher LP, all the way to arbitrary large P. So you start with L6. So the statement in L6 is the following. You can take initial condition, arbitrary initial condition for the cubic NLS defocusing in L6, which is smooth. And smooth means that few derivatives are in L6, not more than that. Right? Few derivatives are in L6 or just smooth, okay. Then the solution of the nonlinear equation will stay in L6 for all times. It grows as a function of time, but it stays in L6 for all times. So then by iterating this argument, we can actually prove that for every LP, the same is true. So if you start with initial condition in LP, if you have enough regularity, then the solution will stay in this LP space. And the only exception is P equal to infinity. So in other words, no matter how P large is, which means no matter how slow the solution is decaying at infinity, you get global existence if the initial data is smooth. right? So at first sight, this sounds very surprising because it means that the nonlinearity is not able to bring all the mass from all over the world into a finite region in a finite time, which means that the nonlinearity is not able to do that. And I just try to convince you that it can. So what is the catch? So let me explain the idea of the proof. So first of all, you see, if you start with a quasi-periodic function which vanishes at infinity, no matter how slow, you get global existence, because this is a smooth function. So you get global existence in this case. But as I said, local existence only follows from this previous theorem. Now, how the proof goes? So the idea is, so there are several steps in this proof. And the first one is the following observation, that if you start with an initial condition which is in L6 and which is smooth, then under the linear flow, it stays in L6. It grows like t to the 3/2 in some norm, but the L6 norm remains bounded. It is polynomially bounded in time, but it is bounded. In other words, under the free flow, the solution remains in L6. Now you stick it into the nonlinear term in the Duhamel representation of the solution. And what you see is that the Duhamel term is in L2, because you take an L6 function which is smooth and you raise it to a power 3. So it is in L2. And now, because it is in L2, the whole Duhamel term is in L2, which means that in this kind of situation, because the initial condition is in L6, actually, the first iterate, we have a Duhamel term which is much, much better. It is an L2 function. This means that the nonlinearity can only produce bad guys, but localized, because they are in L2. So what do you do then? You use this fact in order to prove local existence. So you use this to prove local existence. Well, you prove local existence. And now, in order to get global existence, you say, okay, this problem is subcritical, scaling subcritical. This means that I can take the local existence result, give me initial condition, I don't care what. By scaling, I can make the initial condition smaller than epsilon. And then I can prove local existence on an interval of size 1. Once I have local existence on an interval of size 1, I try now to use the fact that the problem is subcritical, energy subcritical. So how do you use that in previous works? In previous works, you use the fact that the energy is conserved, and so you can get good estimates, which can be used to close the equation. So here you try to do the same thing. You use the fact that localized energy is essentially conserved, and also the L2 norm is essentially conserved. So you use all these estimates in order to get a bound on the L2 part, because the L2 part will satisfy an equation which, if it did not have a source term, it would be conserved because it's L2. So you use the fact that there is almost conservation only for the Duhamel term. So you subtract from the solution the linear part, and you only look at the Duhamel term. You use energy conservation for this Duhamel term, or approximate energy conservation. And in this way, you can get sufficient estimates so that in the end of the day, you can get Gronwald type inequality for the mass plus the energy. And from this, you get control of the solution for all times. So, but this argument fails when p is equal to infinity. The reason is, it seems that if you allow the initial condition to have also a support at infinity proper, then in this case, you cannot avoid the situation in which infinite amount of mass will hit the origin after finite time. We don't know if it's true or not, but the proof fails in this case. Okay. So let me skip this. So now I would like to state some kind of problems that are completely open. Basically, I mentioned the key thing. The key thing is that if you have a problem for which you can prove, say, global existence for some kind, for all initial conditions which are, say, smooth, and the solution is growing. The solution in the last example can grow exponentially, and the solution is growing polynomially. Now, the fundamental question is, if you randomize the initial condition on a certain space of initial conditions, if you randomize it, and since the linear problem is much better, can you prove that the solution behaves better on average? So this is something that we could not do so far, even in a single case. So this issue has to do with many problems in statistical physics, in the soft condensed matter, in the formation of condensates, in approach to chaos, and all of these problems are basically hidden inside this question of what is the behavior of the solution for large time at high frequency and at zero frequency when you randomize the initial condition with a proper class. The end.
Thank you, Avy. Very much. So let's see if we have questions. I think everyone has the right already to unmute themselves if they want, right?
So did you look for cancellations?
What?
Did you look for cancellations between the different parts of the solution? Yes, cancellation might make things better, right?
Yes, so so the issue of cancellation is not used in this analysis because we could not use, we did not do it for the, we did not do it for the randomized initial condition.
No, not even randomized. For
even if
not
it,
randomized.
Yes, sure,
Huh?
even, no, but we did not do it. I mean, the main thing that we use is local conservation laws, localized conservation laws, and finite propagation, and the idea of finite propagation speed. We did not enter into the actual behavior of the nonlinearity to use cancellations. The issue of cancellation appears when you do averaging. The issue of cancellation appears in a very nice and general way. Basically, you need to prove that the endpoint functions, endpoint correlation functions, can be controlled in terms of 2-point functions only. And this way, you can, if this is true, then you can derive kinetic equations. And from the kinetic equations, you can find the behavior for large frequencies, for example. But we did not use cancellations at this stage.
Okay. So did anybody try the cancellations?
I think all the people who I mentioned before who use KM theory and require the Diophantine condition did exactly that. So if you start with initial condition, which is quasi-periodic, then you can see exactly which terms contribute, which terms are resonant and which terms are not. And therefore, this is the analysis which what people usually do. But here, the initial condition is not necessarily quasi-periodic. There is a continuum of spectrum.
Okay.
Avy, I have a question about what do you mean by equilibrium?
Equilibrium means that you take the random initial condition to be chosen from Gibbs state, for example. If you want an example of an equilibrium for NLS, it's the function 1. That's equilibrium at 0 temperature.
Okay.
And now, if you want to solve the problem at finite temperature, I mean, all these things are in some sense boils down to the same question. What does it mean to solve a nonlinear equation at finite temperature? So you take initial condition, which is the constant function, and now you add a small perturbation, which is small as you like, smooth as you like, but it is per unit volume. The perturbation is per unit volume. It's small per unit value. And then the question is, what happens to the solution at a later time?
But you know, if you talk about positive temperatures, then I would think about dissipation. I would think about Lindblad equation rather than about Schrodinger equation.
Well, we would like to derive the Lindblad dissipation.
Okay, but it will not come from the initial conditions.
No, it will not come from the initial condition. But you see, at least in some examples, I can show you that dissipation comes out from averaging the random noise. For example, there are examples in which the noise, the randomness is actually time dependent. You put stochastic term in the equation. And in this case, you can actually derive dissipation.
No,
how you derive dissipation? By looking at the averaged equation.
Right. No, this I believe that if you take local averaging or some kind of averages, then for average you will have dissipation.
Yes. So this is one way to try to derive kinetic equations, for example. But this is different from this approach in which you don't put time-dependent noise. Everything is the initial condition. It's just that you don't know what is the initial condition because it is the state of the surface of the ocean.
I have a second question. So you were talking about two conservation laws, energy and mass.
Yes.
Right? So there is also virial. It's not a conservation law, but you have a nice virial relation.
Yes, we did not use that. We did not use that. But I can say more than that. If you take a completely integrable system, then you have infinitely many conservation laws. And so a natural question is whether you can use all of them to prove that the solution remains nice and bounded for all times. So, for example, there is an analog of the lattice NLS, the discrete NLS, which is completely integrable. And so you may try to do the same thing with all of the conservation laws. There are infinitely many of them. But we didn't do it. We don't know yet how to do it.
Avi, is there an approach to the initial value problem for, say, quasi-periodic data by working with rational approximations? Larger and larger fundamental cells?
Not really, because it's equivalent to solving the periodic problem on a volume that goes to infinity, which is exactly what people do in order to get kinetic equations. But they cannot get to time scales which are the relevant ones.
And Avi?
Yes?
Maybe something similar. If you had something which was periodic plus something that was localized, can you really follow the evolution and presumably the periodic solution is going to be to stop being periodic. If the initial data is a sum of a periodic data plus something more localized.
So the truth is that even the problem of periodic plus a localized perturbation, it's not so simple. Because you cannot solve it on a compact domain. I mean, you have to do something else. You have to. So in other words, if I give you the nonlinear Schrodinger equation with an initial condition which is periodic plus a perturbation of size 1, which is localized, can you show that the solution converges to a periodic solution? Or maybe there is an asymptotically periodic solution for the nonlinear equation. It's possible. It's possible that there is a solution which is asymptotically periodic. In other words, there is a defect somewhere in the periodicity, but if you look far away at infinity, you see that the solution is periodic. That's also possible. So I don't even know how to prove this at the moment.
So for integrable NLS, you have, a very rich inverse spectral theory, not scattering theory, but inverse spectral theory. Can any of that be used to address the question of, say, stability of a periodic wave train to a bump?
Yeah, so for example, well, if it is periodic, then again, you can reduce the problem to finite energy. But let's say that you take the completely integrable problem, which is on lattice, say, what it's called.
Ablowitz-Lattice.
Yes, Ablowitz-Lattice, right? So you take this model, Can you prove something better than what we prove by using the fact that higher norms are conserved? Can you prove that in this case, the solution does not grow at all? I don't know. I'm not so sure, because even for the linear flow, there is a focusing. But the difference might be that because it is completely integrable, there is no energy cascade to infinity. The solution remains localized in frequency space forever. So then you don't have a kinetic equation in this case, but this is not known.
Actually, there is a result about local perturbations of periodic solutions. So if you take a Ginzburg-Landau equation then it has a solution which has periodicity of a lattice. It's a Brikosov lattice, vortex lattice. And then you can look at the local perturbation, L2 perturbations, for example. So the energy of the solution is infinite and mass is infinite, as you mentioned, but nevertheless, you have stability.
Now, what does it mean, stability?
Is this a dissipative dynamics, or is it symplectic?
Okay. You're right. This is done for mixed dynamics. You're right, with the not Schrodinger dynamics. You're right.
Yeah. So first of all,
this could be done also for the technique could work also for Schrodinger dynamics too.
Mm-hmm. It's interesting.
Yeah, I think yes.
And because essentially analysis is reduced to analysis on a Brillouin zone.
I think there is some recent works of Hundertmark and collaborators about this problem, as far as I know.
Yeah, this I don't know.
Yeah, so this is the only result which I know. And what they do is they work on the space which is, in fact, on the Hilbert space, which is L2 of the torus direct sum with L2 on R, which describes the perturbation. So you study the dynamics in this direct sum. But this is hard analysis. They use KM theory in order to get the result.
No, but if you have a torus, it means you don't have a local perturbations.
Yeah, no, you have torus, which describes the periodic part of the solution, plus another L2 of R, which is decaying. So this is one way of writing an asymptotically periodic function. So the problem is how to solve a nonlinear equation in an asymptotically periodic space of functions. This was done in the limit periodic, which is a special case.
And Avi, in the other direction, could you make some solution blow up if for some initial data in L infinity when, say, any L2 data would lead to global existence? Would there be some examples?
I don't know how to construct solutions that blow up. In the defocusing case, no, I don't know.
But in the focusing?
In the focusing, I think it will follow from similar arguments. You can use exactly what Siegel said, to use basically the dilation identity or the conformal identities. You can still do that in order to show that there will be blow up. I think this is possible. But if you have defocusing equation and you say, well, I have infinite amount of energy, prove that there is blow up, even if we don't know how to prove even that.
I had a question. Is there an analog to the Strickhardt estimate for quasi-periodic NLS?
We use the Strickhardt estimates for local times and locally in space. For short times we use it. For the global existence in LP. Other than that, I don't know. It's not clear to me that. So if, for example, if you take initial condition, which is infinitely many Gaussians, which is space by distance 1, and you look at the solution under the linear flow, you see that the solution is basically constant near the origin. It grows like t to the 1/2 or something like that. And if you do averaging, even if you do averaging on the initial data, then you see that after time t, you get contributions from all the points at the distance t in one dimension. So it's not clear to me that there is smoothing, any smoothing. The only thing that I can expect is that if the solution is very large at some point, then very quickly it disperses because of the defocusing.
So your methods were essentially deterministic, right? So
What?
so if you
Deterministic, we can prove that things are bad because you can always find initial condition which is bad.
right, so so my question is are there variations of your results where you show with with a probabilistic statement which has better bounds?
No, we could not do it. That's exactly what I pointed out as something open. I don't know how to use the averaging in the nonlinear case so as to get global result, not finite time.
Okay.
Right, so maybe there are no other questions. We can thank Avy again for the beautiful talk and then continue our discussion later. Okay.
Thank you.
Thank you, Avy, and thanks a lot.